Here I select 16 relatively hard questions. If some of the questions I do not select here, but you have doubts, you can ask me. Yeah. I will jump to those questions and explain. Yeah. All right, so let's start. Yeah, I just follow the order. Yeah, but some relatively easy questions I skip. So if I skip, but you feel you need to ask me some questions, you just, type in the chat area. So I will find time to explain. Yeah. All right, so let's start. Our first question. That is the question number 1. Yeah. So this question, let me give you some basic information we consider. Yeah. Here you can see the coefficients. The coefficients A0, A1 are unknown, not given. Yeah. When it is unknown, consider Horner's rule. Because the Horner's rule usually give us the best solution. Yeah. All right. And but when the coefficients here, I just use the general case. Yeah. When the coefficients are known, okay, yeah, then Horner's rule may not give the best solution. Okay, yeah. In this case, Horner's rule may not be the best. Our question number 2, that's the example, may not be the best. Yeah. You need to take advantage of its special structure. What kind of special structure? For example, monomial. Monomial structure or binomial structure. Binomial. Is there R? Yeah. Yeah. Structure. Yeah. All right. Yeah. So usually that's the basic way we do. Yeah. All right. But here, another special part in this question, other than the Horner's rule, look at that x squared. Yeah. And each term, it's a power of x to the 2k. Okay. That is just x squared to the k. Yeah. This special structure you also need to consider. Okay. Yeah. So that means you need to spend one multiplication for x squared. Okay, yeah. But only once. Yep. After you calculate x squared, you can reuse it. Yeah, only use it once. Do not waste too many multiplications because you already have x squared value. You just use it repeatedly. Yeah. Keep that in your mind. Yeah, but once. Okay? Yeah. So consider these factors, then connecting the dots. Yeah. Put these useful information together, then you try to find a solution. Okay? The main points are here. Yeah. All right. And I give you the, reference in our notes, and you can, this is in Module 1, Part B. Yeah. So if you want to study, so this topic, Module 1, Part B. Yeah. All right. The second question, this one, yeah. Similar topic, yeah. But this time you can see that is the special case, right? Yeah. A0, all the coefficients are very special structure. So this time, if you just use the Horner's rule, that may not be the best way. Yeah, because you didn't take advantage of its special structure. Yeah. The special coefficients may bring you some very special structure you can take advantage of. So here, yeah, you need to recognize the coefficients. Its structure connect to Pascal's triangle. Pascal's triangle, yeah. And this topic, yeah, because I talk about it in the notes, so you can go to Module 1, Part D.2, and the page 6. But if you look at the page, look at my annotation version. Yeah. Because the PowerPoint, original PowerPoint slides version, I do not have this information. Yeah. I wrote it in the annotation page. Yeah. And also, I also talk about it in Module 1, E.3. Yeah. In that one, when I explain a question, I also talk about that, Pascal's triangle. Pascal's triangle, and plus, if you only know the Pascal's triangle, that's still not enough. Then connect to the binomial formula. Binomial formula. Okay, binomial formula. And plus repeated squaring technique. Okay, yeah. So you need knowledge from these dots, connecting these dots. Okay, Pascal's triangle, binomial formula, repeated squaring. These three dots, connect them. Then you can find the best solution. All right, yeah. So that is question number 2, yeah. Next one, question number 3, yeah. So this one, we use a important result, use a result from, yeah, I explain in module 3 part C, in this place, after I explain project, then the last part, I explain a previous topic. Yeah, actually that topic is from module 2, part E.3. Yeah, because in module 2, I ran out of time, so I didn't explain this topic. So I delay it to module 3, part C. Yeah. Yeah. So you should go to this place. And the video, the notes, details is here. Okay. Yeah. And in that place, we prove the power function, this is n to the d, yeah, with d a positive number. So yeah, here, this is the d number. D equals this 1, 2, 3, 4, 5, 6, 7. Okay, that d. And we prove this function belongs to little o of a to the nth. Okay, yeah, with that a, the base, a greater than 1, right? Yeah, check that. This is a. This base number, this is our a. Do you have this a greater than 1? Look at that. Although many 0 after decimal point 1, but still greater than 1, right? Yeah. This little o, what's the meaning of this little o? Okay, the limit when n goes to infinity, n to the d over a to the n, the limit equals 0, right? Yeah, by L'Hopital's rule, right? So L'Hopital's rule. Okay, yeah. Use this example, this result, and try to answer this question. Okay, yeah. Yeah. So that's number 3. Yeah. Number 4. Yeah. Here, we compare these two functions, and actually we talk about that. Yeah. So here, we also talk about, we compare the log function and n to the d with d positive. Yeah. So here, that's the case, right? This time d equals this number. Okay. Yeah. We talk about this topic comparison in the same place. Yeah. Here. Yeah. In the same place. Yeah. But this question is slightly different. Yeah. Because this question, we have this n is a fixed number. It's not a variable, all right? It's not a variable. Yeah. That means you need to plug in to each formula. Okay, yeah. So plug in to each formula and do calculation. Okay. And compare. All right, yeah. And some students may want to use calculator to do the calculation. But the problem is this number is too big for the calculator, right? Look at that number. Yeah. Too big for a calculator. So your calculator may not be able to handle it. Yeah. I would like you to use algebra properties to do the calculation. So this part, yeah, algebra properties. Okay, for logarithms, for power function, yeah, you know, one is for logarithm and power function. Okay, yeah. All right. So then you can find the answer. Yeah. All right. Question number 6. And also question number 7, because they are quite similar. So I like to put them together. Yeah. And actually, this is a continuation from the previous example. Yeah. Because the knowledge we use closely related. The knowledge we use, that is here we use the concept we used here, the order of growth. We compare the order of growth for certain functions. Yeah. Here, for one is because we need to look at the log function, and another power function, and a third exponential function. Yeah. Here you can see all the expressions related to these three types of functions. Yeah. All right. And the reference still the same as the previous one. So that is, so for the reference, still that module 3C, and that's basically module 2 E.3. Okay, yeah. And here I like to point out the fact 1. Okay, yeah. So that is the order of growth of the exponential function a to the n is higher than any than that of any power function. Yeah, so we know just d positive. So that's fact number one. So when you compare fact number two, the order of growth of the log function is lower than that of any power function d positive. Second fact. Okay, all right. With these two facts, so then you can do comparisons. Yeah, but here you also, because some students feel this part pretty tricky. You know, log function is at a denominator, right? Yeah, so that's a little special. Yeah, all right. And so here, one way to consider. So one way to see the order of growth better is, yeah. Can you imagine that the log function is approximately n to the epsilon power? Yeah, I hope. So here we borrow that epsilon from calculus. Calculus, you know that, epsilon delta language, right? Epsilon delta language. Yeah. Although I mean, I do not ask you to be familiar with epsilon delta language. Here, this special epsilon we mean epsilon is greater than 0 and less than d, d, for any positive d. Yeah, so that epsilon, just a special symbol, it has this special property. First, it must be positive. It cannot be 0. It must be positive. Second, it is smaller than any positive number, any fixed positive number. Yeah. So you use this property, special property, for that epsilon. Then when you compare with this one, yeah, because this is d, right? This d equals this very small number. It's a fixed positive number, right? Yeah. Then you can say that epsilon, because here logarithm approximately equal to n to the epsilon, but you can comfortably say that epsilon less than that d. When you do comparison, you compare epsilon and d. Which one is smaller? Which one is larger? That will be easier, a little easier, right? Yeah, so that's some special way to deal with functions involving log function. Also here, if you use this special method, now look at this. N over log of m that special form, can you replace the log by n to the epsilon? Right? Yeah, so this time n to the epsilon, and you do simplification n to the 1 minus epsilon, right? So the exponent number is 1 minus epsilon. Okay? And because epsilon is positive, right? So 1 minus epsilon should be less than 1, right? So think about that. Yeah. Very close to 1, but strictly less than 1. When you do comparison, you can use this inequality. Okay? Yeah. Then, but you also, when you do simplification, because you need to do simplification for some of the formula. When you do simplification, so drop the minor terms. Only keep the major dominant term, okay? Major dominant term. I hope you know the meaning of the minor terms, major dominant terms, right? Yeah. For example, for this one, you can drop the minor terms, right? This one, you can drop the minor terms, right? This one, you can drop the minor terms to do simplification. All right? Yeah. Here, this one, yeah. So if you use the epsilon way, approximately n to the 1/2, right? Times n to the epsilon. After simplification, n to the 1/2 plus epsilon. The exponent number is 1/2 plus epsilon. When you compare some order of growth. Yeah. So you have the explicit expression for the order of growth of this function, 1/2 plus epsilon. That's the order of growth number you can use in your comparison. Okay? Yeah. All right. So here I just give you one suggestion. Okay? Yeah. Although it is a little abstract, yeah, but yeah, sometimes we need to use some abstract thinking. Yeah. Yeah. Like this. Yeah. All right. So that's these two questions, number 6, number 7. Yeah. All right. Next one, number 13. Yeah. So I skipped several questions. We jump to number 13. Yeah. For this question, because we know the golden ratio, some students may notice that the definition of the golden ratio, we have the concrete specific number. Okay, this is the number behind it, the symbol. Yeah. So some students may like to plug in calculator. Yeah, that's one way. So, yeah, use calculator. All right. Yeah. So that's one way. Yeah. Yeah. To tell you the answer. Yeah. But my intention in this question, I like to use our method in module 3, part E.1 on page 2, annotation version. Yeah. In that page, we use the properties. Yeah. We use the properties of the golden ratio phi. So what properties? These two properties. One equals phi squared minus phi. Okay. Another property, phi squared equals 1 plus phi. Yeah. We use these two identities. We can simplify. We can simplify this expression by degree reduction. Yeah. That's the way I like you to use. So you try your best to use this way, all right? If you can, if you feel, so you know how to use this method. If you do not understand, the last thing you can do, this calculator way, okay? Yeah, because you couldn't get it. Yeah, so this simplification way, algebra-based simplification way, you do not know how to do it. So the last thing you can do, use the calculator. Yeah, use some, just do calculation. Which expression gives you the closest number? Then you choose that one, okay? The closest one. Because when you use calculator, you may not get exact number. Yeah, but the closest one should be the best answer. All right? Yeah. So that's this question. This question, question number 14. Yeah. If you know the formula for the Fibonacci number, it is easy. Yeah. But sometimes, because some students, they, as I know, so they do not study the notes. Yeah. Because when I look at the video watching rates, the view numbers are very small. The view numbers, comparing with the number of students in our two classes, very small. That means many students, they do not watch the videos. Yeah. If you do not watch the videos, you may not know the formula. You need to know the formula of the Fibonacci numbers. Right? Yeah. Otherwise, if you don't have that knowledge, simple knowledge, then you may feel very hard. Yeah. How can I do this? Right? Think about, how can I do this? Yeah. And that is in the reference, module 3, D.2 in our notes. Yeah. Yeah. If you know it, answer very simple, straightforward. Okay. All right. This one is pretty hard. Yeah. So this one is pretty hard. Yeah. Because this expression. Yeah. If you use the formula for the Fibonacci numbers, that's not enough. Yeah. So that's not enough. Yeah. All right. So here, let me give you the direction of thinking to find the answers. Yeah. Some of you may apply the strategy try some small numbers for n. Okay, yeah. And see if the statement is correct or not. Yeah. All right. But after you try, if it's not true, then your answer is very easy. All right. But if it is true, but you do not know if the statement is still true for when n is a large number, right? Yeah. So that part you may not feel confident to say if it is true or not, right? Yeah. So this question, I designed it to practice the mathematical induction. This method, yeah, it's designed to give you a chance to practice mathematical induction. Okay, yeah. And so this topic, the reference is in Module 3, E.2. Yeah. In this part, I explain how to use mathematical induction and use it to prove the general case of the Fibonacci number formula, the general case. Yeah. And in that one, we check the base case. So when n, for the smaller numbers, this is the base cases for the mathematical induction. Base cases. Okay? Yeah. After that, we make induction assumption. Make the induction assumption. Okay? Step number 2. Then, step number 3, the most important step, the critical step, step number 3. Okay? Yeah. So when you do step number 3, oops, sorry. Here, let me give you the most important formula or transformation of the formula for this last step here. Yeah. So, but first you need to know the basic way to use the induction method. Yeah. Then I give you this special technique. Yeah. So you can complete it, the last step. All right. First, let us introduce a notation for this expression. Yeah, here, let me just use Sn equals our targeting expression formula, this one. All right. Sn, okay? Yeah. All right. Then, because in step 3 of induction, step 3, yeah, we need to consider Sn plus 1, right? Sn plus 1, that is phi to the 2n plus 2. Yeah. Yeah, because you consider 2 times n plus 1. So 2n plus 2 plus 1 over phi to the 2n plus 2. You consider, you want to show this is, so the goal, you want to show this expression, it is also a positive integer. Okay, yeah, also positive integer. All right. Yeah. All right. Yeah. To show it here. All right. So look at this. Yeah. Look at. Okay. Yeah. Look at this expression. You know, this is Sn. Okay. Times. All right. So let's do multiplication. Multiply through phi to the 2n plus 2. Okay. Plus. All right. All right. Yeah. 4 terms like this. Okay. Then let us group them. Okay. The first group, okay, this one is our Sn plus 1, right? Yeah. The second group, these 2 terms, oh, sorry, no, not that one. The 2 terms in the middle, these 2, yeah. So let us do some simplification. 2n minus 2, that is this one, plus 1 over phi 2n minus 2, right? Yeah, that's this one. And by our notation, that is phi, S sub n minus 1. Okay? All right. So here you can see this identity give us, all right, Sn plus 1 equals S2. Yeah, because this is S2. Sorry, S1, right? Yeah. Yeah, because we take away that 2. All right. By definition, this is definition. This is definition. All right. By that definition, S1 times Sn minus Sn minus 1, right? Yeah, look at that. With this expression, can you get this conclusion? Sn plus 1 is a positive number. Can you get that? Right? Yeah. Yeah. So think about that. Think about that. Yeah. All right. First, positive, no problem, right? Yeah. Look at this expression. Positive, no problem. Okay. Then from this expression, can you see integer? And that expression tells you integer. All right? Yeah. That's the information you need if you want to apply mathematical induction. So that's the critical step. If you want to answer this question well, the knowledge you need here in this slide, that's all the knowledge pieces you need. Okay, yeah. If you can understand this slide well, so then you can answer this question correctly. Okay, yeah. All right, so that's question number 15. Yeah. Next one. Yeah. Number 17. Yeah. Given a 5-element array, yeah, and it is known this formula, okay, yeah, and another expression. We want to determine the element that cannot be the median. Yeah, okay. First, the median. Yeah. You know the median, right? Yeah. The median in these 5 elements, the one in the middle, if we sort it, it is the one in the middle. So that is, it is the third smallest, or the third largest. If you look at from the largest side, third largest. If you look at from the smallest side, also third smallest. Yeah. Okay. All right. So that's the meaning of the median in this question. Yeah. All right. Third smallest, that means exactly 2 elements are smaller than the median. Okay. Yeah. Similarly, third largest, exactly 2 elements are larger than the median. Okay. Yeah. All right. So if you find more than 2 elements smaller than some element, or more than 2 elements greater than some element, then you can eliminate it, right? Yeah. Because these 2 properties, if any one of the properties is not satisfied, then you can eliminate it as the median. Yeah. Because this property to describe the median, yeah, can help you determine the qualification to be the median for each element. Yeah. So look at in the inequality this we are given, if you can find some element that cannot be qualified to be the median. Okay. Yeah. Yeah. That's this. Number 18, given an array with 14 elements, what is the maximum number of inversions that the array can have? Inversions, first, I hope you know the definition of inversion, right? So it's a pair of elements. A pair of elements, AI and AJ, in the given array with the property that is I less than j, but the value ai greater than aj. That's the inversion. Okay, yeah. Then, how to answer this question? Because we need to find the maximum number of inversions. Okay, all right. So how to get maximum number? Maximum number of inversions. Okay. Yeah. Here, consider this situation when all the pairs of elements are inversions. Look at this situation when all the pairs of elements are, yeah, that's the maximum possible case, right? Yeah. So no matter how you pick a pair, yeah, anytime when you pick a pair of elements that form an inversion, that's the maximum. Okay, you cannot have more than that. You cannot have the number of inversions more than that. Okay, all possible pairs of elements form an inversion. The question is, can that happen? Can that special situation happen? Yeah, think about that. If that situation can happen, yeah, definitely you need to imagine the special situation of that. If you find a special array, this you have this property. Yeah. Any pair of elements become an inversion. Then you just count the number of such pairs, all those pairs. That's the maximum number of inversions. Okay? Yeah. This one should not be that hard. Yeah. I think if you can do the thinking in this way, yeah, then you can find the solution, find the answer easily. All right. Next question. Number 19. Yeah. So for this question, I like you to use that, yeah, because in module 1, B.2, yeah, and you can look at the page 4 in the annotation version. Yeah. I talk about a counting technique. So that's the counting by reference technique. That technique, all right? Yeah. Because here, we want to count the number of additions, and we know each plus sign corresponds to one addition, okay? Each plus sign corresponds to one addition. But with the dot, dot, dot here, it's hard to keep track of the number of plus sign. Yeah. So we may like to find the convenient reference, and we can count that the number of reference objects. Yeah. Here, each plus sign we associate with either subscript or superscript. Okay, yeah, because the same number. Yeah. Each one we can associate with either subscript or superscript. Okay, all right. The question: can you count the number of subscript, superscript, excluding the first one? B0. Yeah, because we need to create a one-to-one correspondence, one-to-one mapping. Yeah. B0, no correspondence for B0. Okay, yeah. Excluding B0, then the remaining coefficients and plus signs, we can establish one-to-one correspondence. Then you just count the number of subscripts or superscripts. Yeah. Then you can get that answer. Yeah. So that's practice the, this basic simple counting technique. Okay. Yeah. All right. This one, right. First, it is unordered. Yeah, this property. Okay. Second, that K, the total number of elements that are not in place. Yeah. So you know the meaning. Yeah. So not in place. Okay. Not in the right position after we sort it. Yeah. Those K elements are not in place. Yeah. But the question, we want to find the minimum number for that K here. Okay, all right, yeah. First, because that total, before we do any analysis, we know that K should be greater or equal to 0. So when we start, so we already have this, okay, yeah. Then, if K equals 0, that means there is no inversion, right? That means all elements are in place, right? Yeah, because the number of elements that are not in place, that's 0. It means all the elements are in place. That contradicts to the condition unordered, because it becomes ordered, right? So that's a contradiction. So this case cannot happen. All right. Yeah. So K must be greater or equal to 1. Yeah. Next, think about, is it possible that K equal to 1? That means only one element is in place. No, it's not in place, sorry. Yeah. All elements are in place. So only one element is, yeah, because not, our definition, not in place. Okay. And all the remaining elements elements are in place. The question, is it possible? Is this case possible? Yeah. Try to imagine. You place n-1 elements, remaining means n-1 elements in place. Okay? Yeah. Then you only have last position left for that one element. Can that element not in place? Right? Think about that. Yeah. If this case not possible, then consider k equals 2. Okay? Think about possible or not. Or not. Okay? Yeah. So that's the way to do the thinking. Okay? Yeah. All right. Yeah. So that is question number 20. Yeah. Yeah. Let me see. Yeah. If. Yeah. So. Yeah. We have 3 minutes left. Yeah. So let me just say something about question number 21. 5-element array, and we know X3 is the median. If it is the median, we know its position is known. Its final position is known. Okay? Yeah. If it is known, then we don't worry about it, right? Yeah. So that means no matter how we arrange the other 4 elements, we can always place X3 back to the group in the right position. Okay? Yeah. So in that observation, that means we only need to sort these 4 elements. Okay? So we can take away X3 in the sorting. Okay? We can take it away in the sorting. Yeah. Because we know the smaller the size of the array, then the fewer number of comparisons we need. Okay? If we take away X3, then we can use fewer number of comparisons. And it doesn't hurt we take away X3, because after we sort it, we can always place X3 back. Okay? Place it at the right position. Later. Right? During the sorting, we can exclude it. After the sorting, we can put it back. All right? Yeah. So here the issue is how to sort 4-element array. That's the question. The question, how to sort a 4-element array. Okay, Yeah. So that is a topic in our module 4, part 8.3, but I didn't explain it. Okay, yeah. So I didn't have time to explain it. Yeah. All right. So you can try yourself. If not, if you cannot do it, next time I will do it. So on Wednesday, next time when I start, I will solve this problem for you. Okay? Because it is in our topic. And for 8.3, it is there. I should complete that topic first. Yeah, but today we run out of time, so I have to stop right here. And the next time, let me complete the remaining 5 questions. So question from 21 through 25, the last 5 questions of this assignment. All right.